Okay, we have now the recording. Okay, so as always, you have opportunity to ask your questions. If you have any, be brave, don't be shy, because questions is the best part in education. If you have any questions, just don't be shy.
Boris Borisovich, excuse me, I'd like to ask a question, a general one, about the procedure we use when we are to find some constants, for example, in a Wiener process or in a martingale. So what's the strategy? So basically, we should use either expected value or variance to do that. But is there like a plan of how to find those constants that always works?
Hmm. The question is a little bit different for martingale. So question how we can find, so it's a little bit general, how can we find constants. So we need to find constants, we need equations. So the answer is equations. To find some constant, you need some equation. That's a general idea. So what can provide, what is the source of equations?
The
In the case
properties.
of, in the case of martingale, you have a property that expected value of future value of the martingale. Let's suppose we work in discrete time is equal to current value. So this equation may provide us equation for a constant. So we can have equation for a constant. In the case of Wiener process, we have properties, and basically some properties, these properties can also provide constants. The most important one, I think, which is the closest one to equation, that difference of Wt minus Ws should be normally distributed with mean 0, and variance T minus S for S lower than T. And that basically I have two equations that expected value should be 0 and variance of this difference should be T minus S. So basically your question is a little bit general, and basically in mathematics, how do we, so it's question, how do we find constant? We may guess them and prove that they satisfy some equation. We may honestly solve equations, but that's too general.
Okay, anyway, you've answered my question, so thanks.
So if you have any questions, don't be shy, because I'd like to answer them, but sometimes it's easy to answer something that is in this or that problem. I'm stuck. I don't know how to continue. And for a particular problem, the answer will be, I think, more useful. Okay, let's recall what we have done during lecture. We have introduced informally stochastic integral, Ito's integral. And let's once again build intuition. Let's consider one more example. And then we will provide not maybe a honest definition, but idea of a honest definition, because it's too, I think, mathematically intense to be honest, because we need a lot of things to cover if we'd like to introduce stochastic integral honestly in all the rigor. So I will add rigor, but we still will have some gaps in the formal definition. So, okay, intuition. Once again, I recall that if I consider an integral from A to B of some stochastic process AU dWu, so the meaning of this random variable, so the result is a random variable, and the meaning of this random variable is just profit, net profit, if Wt is interpreted as a price of some object at time t, price of some object at time t, and at is interpreted as quantity of objects I have at time t. I have at t. So basically, the idea that this integral is interpreted as a net profit of some trading strategy. We may think that AT is a trading strategy. Okay, so let's provide, oops, my page is finished. So I will go on the next one. So let's consider AT like, I don't know, 2 if t is less than 5, wt squared plus 7 if t is greater or equal than 5. And I would like to find an integral from 0 to t, au dwu. What is this value? This is an exercise. So first I would draw, this is the price of my object, of the object. It's represented by wt. We ignore, so for us it's a little bit abstract, negative price. Okay, just work as with positive. And the quantity, the amount of number of objects we have. This is t, this is at, it is 2. And then we buy or sell. I don't know what happens because we buy. Oh, we are sure we buy. Yeah, because wt squared plus 7 is obviously greater than 2, so we buy, obviously, in this case, but it may happen that we sell objects. Okay, so AT is the number of objects we have, WT is the price. What is the net profit? So we need to consider two cases. So either the moment T is before 5, either T is later than 5. So in first case, we just have two objects and we do not do transactions. So in the first case, if T is between 0 and 5, let's imagine that T is greater than 0. So in first case, we do not do transactions. We just have two objects in the beginning. We have two objects at the end of our integral. And so what is our profit? How we can calculate it?
Boris, may I ask a question? Why wt squared plus 7 is a horizontal line? Because wt is actually changing.
Sorry, double, yeah. So it's a little bit hard, w5, I meant. Yeah, you're right, because otherwise we need a more brutal theory. We will do something with it, but for the moment, let's fix it. Yeah, you're right, you're completely right. Okay, if I have two objects, what is my total welfare at the beginning, at time 0? What is my total welfare at the beginning? 2 times W0. What is my final welfare?
2W0 plus 3W5 squared plus 7.
No. Imagine that, okay, if it's too hard with parameters, so let's start from 0 to 3, AU, DWU. So let's start first with fixed limit fixed boundary. Okay, so it's just 3. If it's a little bit hard, then let's fix for the moment. So what is my initial welfare? If I have two, I don't know, 2 cups, and each cup is worth W0. So my total initial welfare is 2 times W0. What is my final welfare at times 3? Yeah, Alexandra is right. Is 2 times W3. Yeah. So basically, my final welfare is 2 times W3 because I have 2 cups. Each cup is worth W3. And so I subtract my initial welfare, 2 times W0, final welfare minus initial welfare. But we know from the properties of Wiener process, W is Wiener process, that W0 is 0. So it's just 2 times W3. Okay, let's consider another endpoint. So let's consider endpoint 7, AUDWU. So what will happen? At the final moment of time, now will be 7. What will be my welfare at the endpoint? I will have how many cups, and what will be the price of each cup?
7 multiplied by that W, 7 squared plus 7.
So this will be the amount of cups I have. So it will be W5 squared plus 7 quantity multiplied by final value. Final value will be W7. Subtract. What should I subtract?
To W0.
I should subtract initial value of my portfolio, and I also should subtract investments that I made. At time moment 5, I should buy or sell cups.
Buy.
I should buy. So I subtract. How many cups should I buy at moment 5?
V quadrate.
V.
V in the power of 2 plus 5.
I should subtract. So sorry, it's T. I have sorry. It's remaining. Sorry, it's W5. So I should buy W5 squared plus 7 minus 2 because I have already 2 cups. And for each cup, how much should I pay?
W5.
W5, exactly. Okay. Any questions? Okay, Alexander, thank you. Don't be shy. If it's not clear, say something. So if it's clear, say something, because otherwise it's a crazy idea. When you are silent, it's boring. So if you are, I don't know, walking with a dog, so just say it. I'm walking with a dog. That's fine. It will be more funny. Okay. So in general, in this case, integral from 0 to t, AUDWU will be a function. I should consider 2 cases where the t happens before moment 5, when I should buy cups. In this case is 2WT. And if t is greater or equal than 5, then I will have this sum. This will be W5 squared plus 7 times WT minus W5 squared plus 5 times W5. Yeah, everything is fine?
Yes.
So that's just the general answer for this integral for t greater than 0. So first,
why there is no sorry, because 7 minus 2 is 5. Yeah,
because -2 it is 0. We should subtract initial welfare, but as my integral left endpoint is 0, so I subtract 0. But in general, yes, if it was integral from 1 to t, then I should subtract 2 times W1. Okay?
Okay, thank you.
Okay, so now we can calculate a stochastic integral for jump processes, like that are constant, but sometimes they jump. So for these processes, the stochastic integral is very simple. It just coincides with intuition, and nothing is. So we have no doubts. Okay, let's consider a more general case. So let's try to integrate something like, so our goal, calculate integral from 0 to t wu dwu. That will be our goal. Once again, if you'd like to have a, so I will not define it rigorously because of I have only 6 lectures for the whole stochastic calculus course, so sorry, it will be less rigorous approach. So if you'd like something that is rigorous, then you can go to Baldi or Shreve or Steele or even Zastavnyak. That is the easiest one. So any book is okay. So if you like something with foolproof approach, then okay. So our goal to calculate this integral. What we will do? We will. So it requires me to have both price and number of cups be like WT. So this is price. So this is price is WT. And WT is a quantity of cups I have. So it's a quantity also. So something like this. Yeah, so in this integral, WT is price of a cup and number of cups I have.
These two processes are different, right? They're not the same.
No, they're the same. The same.
So how the process quantity evolves is just the same how the process of price evolves, right?
Yeah. So if the price of a share is 2 rubles, you have 2 shares. If the price is 5 rubles, your financial strategy says buy 5. So if the price is 1/2, so you should have 1/2 of a share.
Okay,
Suppose they are infinitely divisible and so on. Okay, so it's crazy financial strategy. The higher the price of an asset, the more you have. The lower the price, the less you have. So, and the integral has a meaning. What is the profit of this strategy? It's a crazy strategy. I don't advise it, but just to be able to calculate stochastic integrals with some reasoning behind. So to make it more intuitive, how we can calculate stochastic, not just as a blind limit. So it has a meaning. Okay, so now let's go to limits. What I will do, I will divide my interval from 0 to t into n small segments, let's say of equal length. So in a rigorous definition, the length of these segments may vary, but for me to do calculations, to speak about limit, I will say that delta t is t divided by n. So I have divided a big segment into n small segments of equal length. In general definition of a stochastic integral, the maximum length should be limited, but this will be the main, so this is the only point where I will not be rigorous. So I will use equal small segments, but in general definitions, the definition of stochastic integral, they are not always equal. So this is one point, one place where I'm not rigorous. For simplicity, I will assume like this. Okay, and now let's be rigorous. So we can calculate approximation. We create approximating jump process. So I will do transactions only at these points of time. So I create an approximation. IN is approximation for my integral from 0 to t wu dwu. And in these approximations, I don't trade my cups continuously, but I do transactions only at these only at 0, delta t, 2 delta t, 3 delta t, and so on. Okay, so I only buy and sell cups at these moments of time. Okay.
Okay.
And now let's calculate En. So En, it's a process with jumps, which is constant. I have constant amount of shares, of cups, of objects between trading points. And so we can calculate this stochastic integral using our just intuition. So let's once again I may zoom. Yes, zoom. This is delta t. This is 2 delta t. This is 3 delta t. So, and I will specify number of objects I have. So at this moment of time, I should have W0, and I can do this. So I have W0 object. At this moment of time, according to my original integral, I should have Wt over n objects. It may jump, yeah. It may be lower, it may be bigger. Maybe Wtn is positive, maybe it's negative because it's the winner process. But the number of objects I have can jump only when I trade, only at trading points. So the next one will be W2t over n, and so on. Then once again I trade, I buy or I sell. Okay, so the number of objects will not be changing continuous. The price will be changing continuous, but the number of objects I have will change by jumps. It will be constant jump. I trade, I buy, or I sell. Then it will be constant. I trade, I buy, or I sell. Okay. Okay, Alexandra, thank you very much. So don't be shy. Just say yes. It's not difficult to write plus, minus in chat, or just say, yeah, we are happy. Are you happy?
We're happy.
Oh, that's great. Okay, now let's calculate our profit. So at time 0, my initial welfare, I have minus. Why minus? Because I should subtract initial welfare. So it's minus W0 times W0. because this is the price, this is the quantity. Okay, then I should buy, so I subtract at time of the first transaction, at this moment of time, what is the price of my cup? The price, what we are doing, what is our goal?
The price is WT over N, no?
Yeah. At least one guy is alive. Yeah, the price. So our goal, remember, our goal is to calculate this stochastic integral. So this is the price. Okay, yeah, the price is WT over N. And how much should I buy? I should buy this difference, amount I should have minus amount I have. So amount I should buy is WTN minus W0. Yeah, this is once again price. This is quantity I buy, quantity I should buy. Yeah.
Yes.
What will the price of my cup at moment 2 delta T?
2TN over N.
Yeah, W2TN. What is the quantity I should buy?
The difference between 2TN and TN. By the way, Boris, why do you use minus instead of plus, for instance? Does it matter?
You write plus. If you write plus, then you should change. So imagine that I buy. You may imagine that you sell, but in this case, so if you to be more intuitive. So I can do with formal definition, but it's boring. So, but you may think that you sell. So if you sell, then you will have a plus. Yeah, you will have plus price, and when you sell, the how many objects you sell. You sell what you have, W0 minus the amount after the transaction. So the result from mathematical viewpoint will be the same. Yeah, so it's like cell interpretation, and this is by intuition, but basically that doesn't matter whether you add, because you should add with minus or subtract with plus. Okay.
Okay, thank you.
Okay, so let's go on, and the last term will be minus WNTN, because I have n segments, NTN, multiplied by WNTN minus WN minus 1 T over N. And there will be a last term. I have a big portfolio. Yeah, I have a big portfolio, and I can like sell the whole portfolio. Yeah, these are transactions to maintain the number of cups required by my trading strategy, and the final value of portfolio I should add it with plus, and it will be WT multiplied by WT, because the quantity in my strange strategy equals the price. Okay.
Okay.
Okay, so if I write the same thing with sum, it will be one exception, WT squared minus sum I changes from 1 to n, WITN, WITN minus WI minus 1 TN. Yeah, it's the same integral. And basically, we need to let n tends to infinity. So basically, we need to calculate limit of this quantity. In general definition, it's a little bit more tricky, because we should not work only with constant deltas, but with deltas which may be different, but maximal length of delta should go to 0 in the general definition of stochastic integral. But in our case, let's omit this figure and let's pretend that all steps are of equal length. And with this assumption, with this simplification, we are on a rigorous ground.
Boris, could you please once again explain two things? Why do we add the last term WT multiplied by WT, and why don't we include W0 multiplied by W0 in the sum? Because the index I
Okay.
first of all is 1.
Because our W0 is not an arbitrary price, it's a Wiener process. So we integrate with respect to Wiener process. So WT is not any process, yeah? And W0 is a Wiener process, and Wiener process has 5 assumptions. And among these 5 assumptions, there is something like continuous trajectory. So we don't care whether we take the limit from the left, limit from the right. So we have continuous trajectory. So the price has no jumps. So this definition is correct. It's so we have no problems with discontinuities. And one of the properties of Wiener process, I don't remember which one, first, second, doesn't I don't care. It was that W0 is 0.
Okay, yeah.
So that's why I simplify. Okay, why should I have? Because what is the profit? Profit is initial wealth plus final wealth final welfare. No, it's with one L here. With one L.
So the last operation actually reverses what you've done before. So if you buy, the last operation we sell, right? And vice versa.
Yeah. So this term is a final welfare. This term is initial. Okay.
Okay, thank you.
Why do we add the last term? We sell it. Yeah, you may think that in the beginning you buy the portfolio, you make investments, and then you sell portfolio, and this is your. You may sell it or not sell it. It just the idea that what is the profit if you have some. So if I have just one cup, from the beginning it was left by my grandmother, so she left me a cup. So. And I'm owning this cup for 2 years. What is my profit? My profit will be final price of a cup minus initial price of a cup, okay? Because to imitate my belongings, one should buy the cup at the beginning and sell it at the end of my period I consider. So just imagine that you have a cup from your grandma. It's like it's your heritage. So, and what is your profit of owning this object? So minus initial price plus final price. So basically that's the same, but quantity changes. Okay. And so now we need to calculate the limit of this sequence of random variables. So we need to calculate the limit of this sequence of random variables when n tends to infinity. And this will be our integral from 0 to t w dw. This is the definition of this continuous honest ethos integral. Okay, what is the problem? The problem is there are many ways in which random sequences could converge. So there is convergence in probability, convergence in distribution, convergence in mean squared. So we need one specific type of convergence. There is convergence almost surely. There are many convergences. So for non-random sequences, there is only one convergence. The sequence is convergent. It was defined in the first year calculus course. The sequence of real numbers is either convergent or non-convergent. We need not to specify in which sense. When we speak about random variables, if you have a sequence of random variables like x1, x2, x3, x4, and so on, we cannot say it converges. We should say it converges in that sense, because there are many senses, and in one sense a sequence may converge, and in other sense the sequence may not converge. So we need convergence in, so the convergence we need is convergence in space L2, L squared. And the definition of this convergence is the following. We say that the sequence converges to some limit. The limit is a random variable. We say that sequence converges to a limit if first, expected value of xi squared is less than infinity. Expected value of x squared is less than infinity. So they belong to this space L squared. L squared is a space of all variables with existing second moment. So they have variance, they have expected value. I don't care about exact value of variance and expected value, but they have. And the main definition, expected value of xi minus x squared should converge to 0 in normal sense, because it's a non-random sequence. So this is the definition of convergence in L2. Okay?
Okay.
So you may, in a second year course, probability course, probably you have heard about convergence in probability. So these are different types of convergence. So just an example, if I consider an experiment, one coin toss, or maybe not. I need a lot of coin tosses. No, I need a lot of coin tosses. I need a lot of coin tosses. So let's imagine that infinite number of coin tosses, of pair coin tosses, and xn is let's say yes, let me think about a simple example to show the difference between modes of convergence. Yeah, let's imagine a variable that is equal to 2 to the power n if n first tosses were heads, then 0 otherwise. Let's imagine such a random variable. Okay, so we have a lot of random variables. We have one experiment. We throw a coin, a fair coin, infinite number of times. And imagine you have something like head, head, tail, tail, head, tail. This is outcome of our experiment. Tail, head, tail, and so on. For this particular outcome, what is the value of x1? What is the value of x2? What is the value of x3? What is the value of x4? For this particular outcome, what is the value of x1?
Two.
2,
Yeah, it's 2. What is the value of x2?
4,
4.
What is the value of x3?
0.
0, 0, and so on. Or if I have outcome t, h, t, h, t, 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 h, 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 and so on, then x1 is 0, x2 is 0, and so on. These obviously are dependent random variables, yeah? And my question, what is the probability limit? You have studied limit in probability. So my first question, xn tends in probability to what? And xn tends in L2 to what? So, and the answers are different, just to show you that for random sequences, there are many modes of convergence, of convergency. So what is the limit in probability? So we observe that probability that xn is 0 is 1 minus probability that xn is greater than 0. Yeah. And this is 1 minus 1 over 2 to the power n. Because to have n consecutive heads, it's the probability is okay. So with higher and higher probability, xn is 0. x100, we are almost sure that it is 0. Yeah. x200 is 0 with very big probability, almost 1. Yeah. So in probability, our sequence tends to
Zero.
yeah. The formal definition from the second year probability course that probability of xn minus limit that the difference is greater than epsilon, this probability should tend to 0. But in our case, that's right. Yeah, that's satisfied. The probability that xn differs from 0 by any small amount, according to this rule, it's 1 or 2n, and it tends to 0. So using definition of xn tends to 0 in probability sense. But in L2, that is not true. That is not true. There are no limits. Why there are no limits? But let's prove at least that 0 is not the limit. Yeah, maybe I will not provide a honest proof, but at least that the limit cannot be 0, because expected value of xn minus 0 squared is expected value of xn squared, and it will be 2 to the power n squared multiplied by the probability of n heads in a row. The probability of n heads in a row is 1 over 2 times n, and it will be 2 to the power n, and it tends to infinity. So at least 0 is not a limit, and we may prove that there are no limit in sense L2. Okay.
Could you please explain what is sense L2? The squared space?
We have the definition. What do we mean by? So there are many sense of what's the probability sequence, the random sequence is convergent. There is a mode of convergence. Sense is in probability or in L2. So for stochastic integral, we need convergence in L2. So what do I say? A sequence is converged in L2. I mean these two properties.
Okay.
So it's a good question. In what sense the random sequence converges? Because in one sense, the sequence random may diverge. In other sense, the random sequence may converge. As this example shows, that this sequence converges to 0 in probability sense, but does not converge to 0 in L2 sense. Okay, there are many like convergence in probability, convergence in mean, convergence in, I don't know, L3, convergence in almost surely, convergence pointwise. So, okay, so we need one simple theorem, basically that is sequence of Chebyshev inequality, that says that if expected value of xn tends to mu, variance of xn tends to 0, then xn converges to mu in L2, and xn converges to mu in probability, basically. When these conditions are satisfied, xn converges to mu in L2 in probability, anyhow. Okay, this theorem. Basically, it's application of Chebyshev inequality. Using, I will not provide proof, but you may try. Chebyshev inequality. Okay, now let's go back to our example. Let's try. So in our example, In, we need to calculate limit in L2 when n tends to infinity. I write again that In is Wt squared minus sum I changes from y to n, well, Wit n minus Wi minus 1 Tn. Yeah, everything is fine. Now we will calculate limit.
Yeah, fine.
Okay, who is alive?
Can you first scroll up?
Yes, I can.
Thank you.
Okay, let's do it. Let's start with some simple example first. So let's consider the following example. Let's consider an example, sum of t over n, I changes from 1 to n, Wit over n minus, so this is not I, this is like some kn, yeah, kn. Just we'll start with something that is simpler. So let's calculate the limit in let's calculate the limit in L2. Okay, I have just replaced one term in my limit just to train a little bit, because if I start with original problem, it's a little bit too hard. Just let's work with stochastic with limits in L2. So I will apply just this theorem. So to apply this theorem, I need to calculate only expected value, variance, check, and be happy. So let's calculate what is the expected value of Kn. What is the expected value of difference of Brownian motions?
It's 0.
Yeah, we should recall that this difference has normal distribution with mean 0, and which variance?
It over n minus I minus 1 t.
It over n minus I minus 1. Yeah, I completely agree. But if you subtract, you will get I will disappear. Yeah, exactly. Alexandra is right. Alexandra, thank you very much. Okay, so expected value is sum t times n times 0, 0. What is the variance? The variance of a sum is the sum of variances plus covariances. But these deltas are independent. Why is they independent? Because if I draw the first, so let's imagine, so I have W, let's say t over n, W 2t over n, W 3t over n, W 4t over n. And this difference, W4t over n minus W3t over n, if I stay at moment 3, t over n, this difference is future increment. And the future increment is independent of everything I know, yeah? So this difference is independent of everything I know up to time, let's say this is time 3t over n. So future increment is independent of everything I know in what happened, yeah? That's some property number 4 or 3 of Wiener process, yeah? So every future increment is independent of past. So these are independent random variables. And if they are independent, the variance of a sum is just the sum of the variances. The sum t over n squared multiplied by the variance of one separate term. And the variance of one separate term is
T over n.
t over n. So I have n times t squared over n squared times t over n. And the limit, if n tends to infinity, is 0. Okay? Everything is fine? Any questions? Alexandra?
No questions.
Okay, once again, maybe the most subtle point in this proof of variance. Once again, WTN, W2TN, W3TN, W4TN, W5T over N. And if I'm here, current time is 4T over N, then W5T over N minus W4T over N is future increment. And these are known random variables for me. WT over N, W2T over N, W3T over N, W4T over N. So these are known random variables at this time. This is future increment. When the time is 4t over n. So in this case, basically, this future increment is independent of what I know, of every possible function of what I know. So when I take cosine of them, add them, multiply them, subtract, the result will be independent of future increment. So in this case, every bracket is independent of previous brackets, and that means all brackets are independent. Okay, so the most subtle point in this proof that all brackets are independent because every bracket is independent of the past bracket. But so future bracket is independent of the past brackets, and every bracket is independent of future and past brackets. So it's a miracle. Okay, so the limit of Kn is 0 because expected value tends to 0, variance tends to 0, and so we have something that stabilizes at 0. So the limit is in L2 is 0. Okay. Now let's go back to our original Rn. So let's calculate the limit of maybe one more example. Okay, let's imagine Mn will be the sum I changes from 1 to n W t I t over n minus W I minus 1 t over n squared. Once again, I calculate expected value, I calculate variance. So once again, what is the limit in L2? Once again, expected value of Mn is n times expected value of Wt over n minus W0 over n. Yeah. This expected value is the expected value of squared Brownian motion is equal to its variance. Variance t over n, it's n times t over n, it's t. And when n tends to infinity, it's t. Okay? Anyone? I'm trying to calculate one limit, but before trying hard limit in, I calculate an, mn, and then we will go to in finally, because we have enough of training before, because it's a hard integral.
Yeah, that's okay, but in the variance, in the brackets, it should be wt over n, right?
No, sorry, I don't get first, second, third. Which step is not clear? Or maybe
Second step, there is n multiplied by variance, and there is in the bracket t over n. Should it be wt over n?
yeah, you're right. Yeah, I agree. Yeah.
Thank you.
Yeah, that's great. Now everything's fine.
Yes.
Okay, and let's calculate variance of mn. Variance of mn. They are independent, so it's like n times variance of one term, wt over n minus w0 squared. It's n times variance of wt over n squared. I recall that wt over n has normal distribution with mean 0 and variance t over n. So I may represent it something like square root of t over n times z, where z is normal 0, 1. I'm standardizing my variable. So it will be, if I standardize, it will be variance of t over n z squared. T over n goes outside variance with a square. So it will be t squared over n, variance of z squared. And when n tends to infinity, I don't care about the variance of z squared. It's a number, so I just don't like to calculate it. And the final answer is 0. Yeah. So we have proven that expected value of mn is t. Variance of mn tends to 0. And in this case, we can conclude that mn tends in L2 to which number? To t. Okay. And now finally we calculate our stochastic integral. Now finally let's calculate integral from 0 to t wu dwu. We have calculated approximate, this is our I. We need to find I. Finally, our main problem, a complex stochastic integral. Our approximation was in, which is wt squared minus sum I from 1 to n, wit over n, wit over n minus wi minus 1 t over n. We need to calculate the limit in L2. Let's open the brackets here. And let's see that it is, oh, for simplicity, let me write w, no, not w, let me write mi, it will be just, no, not mi, m is already used, sorry. Let's say vt, no, vi, yeah, vi will be just wit over n, because I'm bored to write anything it over n. So it is So I need a sum W Vi minus Vi minus 1. If I open the brackets, it will be sum of Vi squared minus sum of Vi times Vi minus 1. And if I look at my previous example, it's almost like this. If you look at previous example, the Mn, it is the sum of Vi minus Vi minus 1 squared. And if I open the brackets, it will be the sum of Vi squared plus the sum of Vi minus 1 squared minus 2 sum of Vi minus 1 squared. I changing from 1 to n. So if I see that these two sums are almost equal, if I just write two sums of Vi squared I ranging from 1 to n, I should only subtract minus Vn squared, the only term that is missing there. Yeah, everything is right. Minus 2 sum, or everyone is lost. Who is with me? Okay, once again, this is this difference, and this is the subtracted term. Yeah, that's okay.
Yes.
Oh, yeah.
But if we wrote like 2 multiplied by sum of Vi minus 1 squared, we would add
Yeah,
Vi.
exactly. Yeah,
Mhm.
we would add. Yeah, you are completely right. Okay, and I know that this limit tends to t. We have proven it. Mn tends to t. So I conclude that sum of Vi squared minus sum of Vi minus 1 tends to t plus Vn squared divided over 2. Yeah? Okay? We have proven it. If this Mn tends to t, then I move Vn squared to the right-hand side. I divide by 2, and I have this is just t times Wt squared over 2. Okay?
Okay.
And finally, my In, I have an answer. It is Wt squared minus the limit of this sum. And the limit of this sum is t plus Wt squared over 2. So finally, we have calculated our first integral, stochastic integral. So that's all for today. Just, I don't like to turn a page, sorry, but I think it will remove all our calculations. By the final, our goal is achieved. We have calculated that integral from WU dWu is just Wt squared minus t over 2 minus Wt squared over 2, and it's Wt minus t divided by 2. So that's our final answer. We have calculated a complex stochastic integral, and it shows us that with stochastic integrals, we cannot just apply our intuition. Sorry, how did you get it? Which one? Which step? So let me write steps. So it was first step, then second step, then third, fourth, fifth, 6, 7, 8. Okay, which step is not clear, Alexandra? Transition 5. So the second term is just written as it is, okay? So what is the difference between these two sums? The first one says W1 squared plus W2 squared plus W3 squared plus W4 squared. The second one says W0 squared plus W1 squared. What is the difference between two terms? The difference between two terms is just the last squared W that is missing here. Wn squared is missing in the second sum of squares. And so I take two big sums and I subtract one term that is missing, okay? Six. So we have this result. Just move this term to the right-hand side and divide by 2. Divide by 2 and move this Vn to the Anna, just move Vn squared to the right-hand side and divide by 2. Okay? 6 is fine. And when I go back to initial question, I see that my initial, so if I look at the first expression, In is just Vt squared minus sum of Vi times Vi minus Vi minus 1. And we know that this is sum of Vi minus Vi minus 1. So that's expression we need to calculate. And we know that I just copied Wt squared minus a copy of it.
Guys, buddies, trying to like clarify what we've done. So first we find like an approximation, right, for our integral, which was for like discrete time. They were like T over N, right?
Yeah, this is our approximation, yeah.
And then we, N converging to infinity, we find like the continuous integral, the continuous value.
Yeah, exactly.
And the value is a random variable.
Yes, exactly. Because this quantity is a random variable. It depends on Wt squared.
Yeah, thank you.
Okay, yeah, the limit of random sequence is a random variable. Yeah. That's all for today. Thank you. See you next time.
Thank you very much. Bye.
Thank you. Bye.
Thank you.